So now what we're going to do is create a couple of additional scenarios and try some transient protection strategies here. So what I'm going to do is create a child of this scenario, and we're going to call this just air valve. So we're going to try an air valve and see if it has any effect. So you might have noticed back in that profile that there was that high point. So we're going to try putting an air valve at that high point. So one of the things that I'm going to touch on now, which is really important when you're dealing with scenarios and alternatives in Hammer, is active topology. So active topology allows you to basically turn elements on or off between scenarios. So what I'm going to do is create a new child active topology alternative, call it air valve, and assign that to our new scenario, active topology, air valve, and then make that scenario current. So what this means is that any elements that we now add in the scenario are going to be inactive in the base alternative, or rather any scenarios that use that base alternative. So let me demonstrate here. So I'm going to go ahead and in this case create a small T pipe here with an air valve at the end. And let's move the label a little bit. And I'm going to enter some properties of the pipe. We'll just make it 400 millimeters and match up the wave speed of the pipe next to it. And we're going to match up the elevation of our air valve with the elevation of the node next to it. So our high point is at 165 meters. We're going to use that as our elevation for our air valve. So in the transient section here, we're going to enter 20 millimeters. We're going to try 20 millimeters as the air inflow orifice, and 20 millimeters as the air outflow orifice. Now I'm just going to switch back to our no protection scenario and watch what happens. So notice that the air valve and the adjacent pipe are now a gray color, which is basically indicating that they are inactive. So we'll see is active is false. So what this means is we basically didn't touch our no protection scenario. So if we were to run this no protection scenario, it's going to act as if the air valve is not there. So this is really useful if you're trying different transient protection methods. You're going to be adding things in, tanks, air valves, and so forth. But you may want to retain the other scenarios that you've already set up. So this is really, really useful for that. So getting back to the air valve scenario. So what we're going to do is let's rename this here, be a little bit more descriptive, 20 millimeter. I'll go ahead and compute initial conditions. And this again is built off of the average day demand scenario. So it's going to use the same setup, which is to say it's going to be an EPS initialized at hour 7. Okay, so that's good. So let's validate the model. No problems of interest. And let's compute transient simulation. Okay, all good. So now let's go to the transient results viewer again, see if we did any better in our profile. Okay, so recall before that the maximum was about 220 in this case. So we did a little bit better, and let's animate it to kind of see the effect of the air valve, paying close attention to this point right here, our high point. So let me pause there. So what happened is it cushioned the transient a little bit. So when back it up a little bit. So when this transient wave reached the air valve, air started to be let in. You don't see the air up here because the profile that we created didn't actually cover the air valve because the air valve is at a T. But basically what's happening is when the hydraulic grade drops to the physical elevation, air valve opens up, lets air in. But you can see that the hydraulic grade still drops a little bit below the high point. So probably we're not letting air in fast enough. But it does help a little bit. So if we continue graphing there, we can see looks pretty good, not too bad. But if we wait a little bit, just fast forward a little bit here. Okay, so right here, we can see similar to our air pocket, or rather our vapor pocket collapse, we have an air pocket collapse occurring from the air that was let into the air valve. And that has a similar effect. It bounces back and forth. And so we didn't do all that much better with the 20 millimeters. So let's go ahead and try, let's try a 40 millimeters. So what we're going to do for this is create a new scenario. We'll call it air valve 40 millimeters, and we'll try 10 millimeters for our outflow orifice to let the air out a little bit slower, so as to cushion, make sure that those adjacent water columns don't come together too fast. So the key here is we want to make sure to choose the right, again, the right alternative for that scenario. So in this case, since we're changing transient properties, we want to choose a new transient alternative for that scenario. So I'm going to go ahead and create a new child transient alternative, and I'm going to call this air valve 4010. Okay, so in that scenario, we're going to choose that new transient alternative and also the initial